That little light suggests that we are live. So we are close to time to starting. We will pause for a moment in order for everyone that's wanting to attend to be able to arrive. And because it's recorded, I don't know that that actually matters all that much. But we'll stick to our time in any case.
Brian?
Yes.
So I'm expecting, I think we're expecting, that some of our results and graphs will change between now and APS. Should I note that at some point so people aren't caught up on that, or should we just go through as though?
Yeah, I think you can say this is the preliminary presentation of the symposium, that there is some data still accumulating and being tested. So any feedback on the materials is great, and all of it is subject to revision, including what the rules are. All right, well, we're at time, so why don't we get started. For those of you that are calling in, welcome. Thank you for attending this. We will very much appreciate the feedback that you have. The purpose of this is to do is two things. One is to do a run-through of what we have so far from the work of the various replication teams for the Reproducibility Project Psychology and for the analysis teams that have gotten through some of the data analysis. As you might have just heard Liz mentioning, this is an in-progress summary. The analytic teams are still working through some of the data, so we expect a lot of the work to be updated over time, including over the next week. But what we'd really like to do is present where we are to the team as a whole and get feedback on the structure, style, and format of the presentations. So what we'll do is we have four presenters: Calvin Lai, Etienne Labelle, Elizabeth Gilbert, and Nina Strominger. And they will introduce each other as they go through, because this is a coordinated symposium. These are highly dependent upon one another. They are not independent talks. I am the chair of the session, and I will begin just as simply as I expect to begin at the meeting, which is to note that this is a project that I think is unique in our field and exciting for me personally, but I think for many of the people involved, in that it is a community-driven project. We arrived at this idea with an interest in trying to understand better reproducibility in scientific research. Many concerns have been raised about the extent to which there are reproducibility challenges, but there is very little empirical evidence. It's a lot of discussion, a lot of theory-driven, a lot of simulation type of evidence, and not a lot of systematic evidence about reproducibility challenges in the field. What is the degree of reproducibility, and what are the predictors of when things reproduce or not? And so the project was born out of that fundamental idea, but also with a recognition that there's very little ability for any individual lab to try to tackle such a question. The only way that we could tackle that kind of question is on a large scale, and it isn't in anyone's individual career interests to easily, at least, to pursue such a big question on an issue that has unclear payoff in the standard incentive structures in science as they have previously existed. So the community gathering around thinking that this is an important issue, there are now 255 contributors to the Reproducibility Project, people that have aided this project in some way. That is a massive community effort. And what it speaks to is that a lot of people see this as an important issue for the field, and they're willing to put in some service and time to do something about it. What will happen in the session when I'm actually presenting this is we'll have a sort of a movie credits screen of all of the contributors' names going by, so we can at least say, these are the authors. And what we have today are four representatives from this large team who will present the background and motivation for the work, the design of the project, where we are with preliminary results, because this is an ongoing project, and we're very much like the people that get involved to a greater extent or at all, if people are so inspired once they see it, and then discuss some of the implications. So I will first hand this over to Calvin Lai, who is a graduate student in the Department of Psychology at the University of Virginia and one of the contributors on the Reproducibility Project Psychology. Calvin.
Hi. Hi there. Yes, so I'll be talking about the background and motivation of the project today. So I just like to begin with an idea. And that idea is classical conditioning, right? So pairings of a neutral stimulus with an unconditioned response leads to the activation of a conditioned response whenever that neutral stimulus is presented. Or I guess
it's your screen sharing, by the way.
My screen sharing isn't working.
We're seeing your slides, your raw slides, not the broadcast.
Oh, 1 second. Okay. Is it good now? Hello?
Yeah, looks
okay.
Good now.
Right. So anyways, in the classical study, right, we have Pavlov who rings a bell every time his dog got food, and eventually he conditioned the dog to start salivating every time the dog heard a bell. Now, when you think about it, why do psychological scientists trust this idea? Why do we trust classical conditioning? We trust classical conditioning because it's an idea that's testable. It's something that's independently verifiable. We can run experiments to test the implications of this phenomenon. We can go get our own dogs, we can ring our own bells, and we can see if our own dogs salivate as well every time it hears a bell. Psychological scientists have run, hundreds and hundreds of variations of this study over and over again, and they found that classical conditioning is reproducible. Classical conditioning works. I bring this example up because it points to one of the most critical features of our science, and that's reproducibility, the extent to which we get the same results when we try to repeat a scientific study. Reproducibility is one of the most critical defining features that distinguishes what we do in science from non-science. So here's an example of a typical research process. You use some methods to collect some sort of data, you analyze that data, and then you interpret your findings, you interpret your results. And when you think of reproducibility, there are several ways you can think about it. At the most narrow way, you can think of simply taking that data and then reanalyzing the data to see if you get the same results. Usually, when you try to run the same analysis, you end up with the same results. So, for example, Pavlov could hand you his data set. You could run the same analysis and see if you could get the same classical conditioning effect. And then most broadly, you can also think of replication in terms of conceptual replication. That's attempting to verify the interpretation of a finding by looking at the same idea using different methods. And of course, this can mean many different things, such as using a different type of manipulation or a different type of outcome. So instead of testing for classical conditioning effects on a dog, for example, I could go to the pet store and get a parrot and see if parrots show classical conditioning as well. Conceptual replications provide insight about what a finding means. Unfortunately, they can often be a little unilluminating for telling us whether the original finding exists, whether it's replicable. Knowing whether or not my parrot shows classical conditioning doesn't tell us very much about whether or not a dog will show it as well. And so the alternative to conceptual replication is direct replication. And direct replication is when you attempt to replicate the original observation using the same methods but with different participants. It provides info about whether or not a finding could be obtained, regardless of how we might interpret the finding. And so we could get our own dogs and try to replicate Pavlov's procedure to see if dogs show classical conditioning as well. Now, diligent use of direct replication is really helpful for assessing out whether or not our findings are false positives. They can often help us prevent engaging in inefficient uses of our resources, trying to get findings that aren't true at all, or at least aren't reproducible. Now, given that utility, you might expect that direct replications are published frequently. But perhaps surprisingly, that isn't the case. And by one recent estimate, as low as 0.15% of all published articles in psychology actually contain a direct replication. And this is particularly shocking because a recent survey of 1,300 psychologists suggests that on average, people want about 20% of journal space to be devoted to direct replication. So it appears here that there's some discrepancy between how things are and how things are wanted to be. So this begs the question, well, why? Why are direct replications so uncommon? The most proximal answer might be that we have incentives for publishing scientific research. And the most exciting science isn't actually replication. What publishing encourages is innovation. It's the stuff that's at the periphery of our knowledge, what we know very little about, and the areas where we potentially break the most ground. It's really exciting to talk about flashy new results, but it's less exciting to talk about another failure to replicate. And so this publishing preference for more positive results and less null results can often lead to unintended outcomes. So here's some evidence from the published literature that suggests that perhaps things are maybe too positive to be true. Danielle Finelli did an analysis of what gets published across scientific disciplines, and what you'll find is that across all these disciplines, the positive result rates, the degree to which hypothesis comes out to be true, is 70% or higher. From physics to psychology, these rates were even higher, from 85 to 92%. Now, consider that our field's 92% positive result rate in comparison to the average power of our actual published studies. Estimates suggest that the average psychological study has a power of somewhere around 0.50 to 0.60 to detect effects. So even if all of the findings that we had were 100% true, we would actually only expect between 50 to 60% of our critical tests to actually reject the null hypothesis. But instead, we get 92%, a whole lot more. So it seems that something here isn't making sense. Something is off in the evidence that we've accumulated as a field. In the medical sciences, they've used statistical simulations to estimate exactly what percentage of published findings might be false. And as you can tell from this somewhat sensational title, these simulations suggest that, at least in the medical science, most findings might not actually be true. And so this raises a question. This is really concerning. What's driving all these false positives? And one additional mechanism identified by Simmons, Nelson, and Simonson is the possibility that we all engage in these types of questionable research practices that might make our data look a little bit more significant at the expense of accuracy. These practices take advantage of flexibilities that we have in data collection and analysis. And it might include failing to report all the conditions that you have in an experiment, deciding whether or not to collect more data based on whether the results are significant, or selectively reporting only studies that you think worked in a paper. So together, these findings suggest that our research literature is not as airtight as we might want it to be or expect it to be. But what's notable about all these pieces of evidence is that they're not definitive, right? The best type of evidence would be to actually go out there to see exactly how replicable studies in the psychological literature are. And so with that in mind, we sought to do exactly that. We designed a project, the Reproducibility Project, with the central goal of systematically and empirically investigating the reproducibility of studies in psychological science. It's not enough to just simulate data or look at patterns suggesting that we have a lack of reproducibility. The best thing we thought we could do was to actually go out, collect data, conduct the direct replications, and see how replicable our field actually is. And to do that, we recruited researchers from all across psychology to conduct direct replications from prominent journals, studies from prominent journals. And without these volunteers, as Brian noted, this project wouldn't be possible. We have 255 volunteers from 64 universities that span 11 countries, all conducting direct replications to help us assess how replicable our field actually is. And all of this is done with two end goals in mind. The first was to understand the overall reproducibility rate of psychological science. Knowing that number can help us get a grasp of how big the issue really is and how much we need to do to really overcome it. And the second is to understand what predicts reproducibility, whether or not a study will replicate. Information about the predictors of reproducibility can inform individual research practice, journal editorial practices, and perhaps ultimately the type of incentive structures that we construct for ourselves in scientific publishing. The more we know, the more we can do to effectively combat irreproducibility in psychological science. And with that, I'd like to give it over to Etienne Lebel from Montclair State University, who will tell us more about the design of the Reproducibility Project.
Okay, great. As Calvin said, my name is Etienne Lebel, and now that we know why we're doing the Reproducibility Project, that is to empirically estimate and understand the predictors of reproducibility in psychological science, I will talk about how we designed and executed the Reproducibility Project. And note that we are still executing the Reproducibility Project, as many studies are ongoing. To do this, I will focus on two major design challenges. The first being the generalizability of our results, and the second, ensuring high-quality replications. Maximizing the generalizability of our results required a careful balancing act between, on the one hand, selecting studies in a way that is maximally representative, which would require fully random sampling, and on the other hand, selecting studies in a way that maximizes participation, which requires choosing feasible studies for which replicators have sufficient expertise. In other words, fully random sampling of studies may drastically and could have drastically reduced participation, whereas only replicating super easy studies, such as online studies, would seriously reduce the generalizability of our results. And so we aim to find an optimal balance between fully random sampling and replicating feasible studies by using a quasi-random sampling approach. And so to do this, Reproducibility Project volunteers produced a list of feasible studies from the 2008 issues of 3 prominent journals, Psych Science, JEP Learning, Memory, and Cognition, and JPSP. The 2008 issue was chosen because it's recent enough that original authors should still have their experimental materials, but old enough to have impact metrics to use as predictors of reproducibility. And so replicators chose a study to replicate from this list. In the case of multi-study articles, the last study was the key target of replication unless it was not feasible, in which case the before last study was selected. And so following this approach, there were 160 studies available. 80 of these studies have been claimed, with 31 replications fully done and fully finalized, with 14 replications done with data collection, and 40 replications started and currently ongoing. Note that 80 studies are unclaimed at the current moment, and we invite you today to consider claiming one of these studies. The second major design challenge is ensuring high-quality replications, which is crucially important to maximize the probability of reproducing true findings, but also important in maximizing the interpretability of replication findings in the event of null results. We employed 5 strategies to ensure high-quality replications. First, we used large sample size that achieved a minimum statistical power of 80%. And so as you can see from the histogram, and these are for the 31 completed replication studies, the overall replication studies were high-powered, with 87% of replications achieving greater than 90% power, with a median power level of 95%. Second, replicators were instructed to acquire original materials from the original authors as much as possible. And indeed, over 95% of replications successfully acquired the original materials from the original authors. And this, of course, is important in order to maximize the closeness between the replications and the original studies. Second, replication teams drafted a standardized replication protocol that was based off of a template that was available. And these replication protocols specified the target sample size, which was based on power calculations, and the sampling procedures to be used in the replication. The protocols also specify the exact procedures and task instructions to be used, specify the exact materials and measures and other details such as scale response options, and also specify the exact data preparation approaches and the exact analyses to be used in evaluating the replication results. 100% of replications produced these protocols prior to data collection. The third strategy that was used, or rather the fourth strategy, was the vetting of replication protocols. And so once the replication protocols were drafted, they were sent to the original authors for review so that the original authors could identify any discrepancies in the methods used between the replication study and the original author, and also identify any other factors that could reduce the probability of replicating the original results. And so the original author would include comments and or issues that may reduce the probability of replicating the results. And also, replicators, once revised, the replicators sent the replication protocol to at least one Reproducibility Project member for review in terms of further identifying any issues that might reduce the probability of replicating the original results, and then sent back to the replicators for final finalization. And indeed, over 90% of replication teams, or rather over 90% of the original authors did vet or endorse the replication protocols, and over 90% of replications were vetted and reviewed by Reproducibility Project members. And finally, the finalized replication protocols were uploaded to the Open Science Framework, a public repository in order to maximize the transparency and accountability of the replication studies. And indeed, 100% of replication protocols were publicly posted prior to data collection. And that's it for the design. I now pass it on to Elizabeth for preliminary results.
Okay. Is that showing up for you guys? Okay, great. So, as Etienne noted, I will be talking about our preliminary results. So, I'll begin by just asking, what might you predict would be our replication rate? Remember, Etienne mentioned that we had very high power, and even if so considering our high power, if every single study that we replicated were, you know, true, and we did a decent job replicating it, you might expect something as high as 95% power. Even if all of the original studies were not replicable, on the other end of the spectrum, you might still expect about 5% to replicate just by chance. If you looked at some of the previous replication attempts in cancer biology, maybe you'd expect something a bit higher than 5%, but still pretty low, perhaps in the 11 to 25% range, like cancer biology got out of some of their top journals. But the answer really depends, at least in part, on what counts as a replication. So there are lots of ways to measure whether something's replicates. And I'm going to present to you three potential ways. One is simply the effect size against the null. So that's looking at p-values and whether the replication p-value is different than 0. The second will be an effect size comparison. And then I'll end with a quick meta-analytic precision estimate. So if we are looking at p-values or sort of the effect against its null, it is important to keep in mind that even this is not as simple as it sounds. You might have interactions, you get a significant interaction, but you know the results don't have the same ordinal direction as the original. But for today's study, I'll just be presenting a very simplified version looking at p-values. So this first graph is just a histogram of the frequency of p-values less than 0.05 for the original study. This graph actually includes 22, even though our sample size hopefully will be 31, like Etienne mentioned, by the time that we present it. But basically what you see here is that for the original studies, every single one of them presented p-values at 0.05 or less. But what we found in our replication attempts was that only about a third of the studies had p-values of less than 0.05. So that blue line is the originals, and this pink line overlaid is our number of replications that had p-values less than 0.05. Well, you might be thinking, okay, but perhaps a lot of the replications had p-values at 0.06 or 0.10 or something that would suggest that they were pretty close. We should still count them as replications. And if you look at the full distribution of p-values, you see there are quite a few that fall at less than 0.02, but there are also a good number, about a third, that are falling pretty far away from that, not even trending. So again, the blue line is the original studies, and pink here are the p-values for our replication. but this graph doesn't tell us a lot about the relationship between the original p-values and the replication. So now I'm going to turn to some scatter plots that help better demonstrate, I hope, the relationship between the original p-values and the replication study of p-values. So these graphs are going to generally look something like what I've got up here now, where on our x-axis we're going to have the p-value of the original study, and on the y-axis we're going to have the p-value of the replication. And these p-values, of course, go from 0 to 1. So start just by doing a, in this graph here, these red lines mark the 0.05 values. So if we had full replication, you would, of every single study, you would expect that all of our dots fell into that little small quadrant on the bottom left there, between 0.05 for the originals and then p the less than 0.05 for our replications if you're using p equals 0.05 as your replication cutoff. And instead what we find is, of course, all of our original studies fall into that quadrant, but our replications are spanning anywhere from right at significance, 0.01 up to yearly 1. It's a little bit difficult to really see the relationship between the original p-values and the replication p-values on this graph because it is all squeezed in on the x-axis. So in my next graph, I'm just going to zoom in so that my x-axis is going to go and just cover this sort of relevant area up to 0.05. The y-axis is going to remain from p is 0.00 all the way up to 1. So if we scoot it over, the same distribution of dots looks something like this. And this allows us to see that there is a small correlation between p-values in the original studies and p-values in the replication, such that if the original p-values were lower, then it was more likely that the replication would also have a lower p-value. And kind of interestingly, these are, of course, very preliminary results, but see here that if you note that if the original p-value was above approximately 0.03, then as of our results right now, none of those studies with p-values replicated. All right. So next, I'm going to shift a little bit and look at a potential moderator for replication. These are very preliminary results. As we mentioned, we only have 31 studies we're looking at so far. But we know that this is on everybody's mind, so I'll go ahead and present it. But this is an ongoing project. These are not our final results. Very small n, so take these with a grain of salt. But if we do the breakdown and we look at what replicated by journal, and as Etienne mentioned, our 3 journals were Psych Science, JPSP, and Learning, Memory, and Cognition. Then what you see here is that so far none of our JPSCs have replicated. But at least a few of our Psych Science and a few of our JEP, Learning, Memory, and Cognition have. So again, what you're looking at is whether the replications fall below that horizontal 0.05 line. And on this graph, our JEP, learning, memory, and cognition, are pink, psych science are blue, and JPS are green. So p-values, of course, as I mentioned earlier, are just one way to look at whether something's replicated. And next, I'm going to turn to a different way, which is effect size comparison. So this, of course, ignores p-values, and it's just looking at the size of any effect and how the original effect study might predict the effect size of the replication. So again, I'm going to use graphs that look a lot like our p-value graphs, where on the x-axis, I'm going to have the effect size of the original study. And on the y-axis, I'm going to have the effect size of the replication. So higher on the x-axis or higher on the y-axis means larger effect sizes. And if we had a perfect relationship where the effect size of the original study matched the effect size of the replication, we would, of course, expect this perfect relationship line. And we would expect that just by chance, about half of our replications would fall above that line, and about half would fall below that line. If the original effect sizes were not overestimated compared to the replication. Instead, what we find is that nearly all of our replication effect sizes fall below that line. So again, these dots are representing the effect size of the original against the effect size of the replication. And you can see that a handful of them fall very close to the line, but only 2 are above it, and quite a few are well below the line, suggesting that the effect sizes in the original studies did tend to overestimate the effect sizes for these studies compared to our application. But you can also see that this lighter black line below our blue line is showing the correlation between the effect sizes. So even though there isn't a perfect sort of replication size, there is a very strong correlation between the original study's effect size and the replication's effect size, such that when the original effect size was larger, the replication's effect size also tended to be larger. And again, I'm going to show effect size by journal. And what we see is that, once again, it appears as, we have the same effect. So a lot of this is repeating information from the previous slide, where it's showing the strong correlation between effect size and original and effect size after. And interestingly, you again see that psych science and JEP, learning, memory, and cognition, are tending to have larger effect sizes in their replication. Another interesting thing to note about this graph is that if you look at this horizontal and vertical dotted lines, this very preliminary data seems to suggest that if the original effect size was below about 0.4, then the replication effect size tended to be below about 0.2. So if your original effect size were 0.4, then your replications our replications so far seem to suggest that you'll get about half or less of that effect size in the replication. And I'd like to end with what we're calling a meta-analysis. We don't know exactly how to interpret this information, but one possible way, given what we've learned from the original studies and the evidence from our application, one possible way to sort of integrate that information would be simply to combine the original effect sizes with the replication effect sizes to get some estimate of the actual aggregate effect size. So this graph is just another way of depicting, and I'll change the colors on this, but that the original effect sizes are in this light gray on the right, and the replication effect sizes with confidence intervals are on the left. And so one way for us to think about this data is to combine this information into an aggregate effect size with 95% confidence intervals. I don't have that graph yet, but it would be a combination of the effect sizes on this current graph and I'm hoping it will look something like this, where we can put up a line indicating 0 effect size, and by combining the replication with the original effect size, get some estimation of whether the 95% confidence intervals for these effect sizes cross 0. So we'd have all of our studies stacked along the y-axis, and then each study's combined effect size along the x-axis. And with that, I am finished talking about our preliminary results, and I will hand it over to Nina, who will hopefully give us some insight on what all of this means.
Okay, cool. So I am on my phone right now, so I'm going to do something a bit annoying, and hopefully that won't give people too much, like, seasickness. I'm just going to hold my phone up to while I go through the slides. I don't think Brian had offered to put it on his screen, but I think it won't work because when I'm talking, I think it will be, his screen would be minimized. So if the visual is not helping you, just close your eyes or look away or something. I don't know. I'm not really going to be showing any pictures, so I don't really think it much matters anyway, actually. Uh-oh. Okay. Okay, so let's step back for a minute. I mean, we were just looking at a lot of data, and now it might be helpful to be reminded of why we're doing any of this in the first place. So there's at least 2 reasons. The first is just to get information about the problem. How bad is it? Is there really even a problem at all? And then once we have that information in hand, there's sort of this supplemental or next step on this question, which is we need to know what practices, so what are the moderators that affect the rate of replication, and this will in turn help us understand what practices might lead to higher rates of replication. If there's a problem, we need to do something to correct it. But I'll just also say that the replication rate itself is not a fatal problem. It's not like there's some number that it would be, and then that's a threshold, and then if it's like, you know, below 80% or below 50%, and then that means like the end of science, right? Although that's an interesting conclusion that one could make. But I think that the best way to think of this is that once we look at the replication rate, we should then titrate our skepticism of published results accordingly. Now, of course, all other things being equal, it would be best to maximize replication rates. And anything less than 100% is, I think, going to mean that we should a call for making systematic replication more of a part of the standard practice of what we do as scientists. But I mean, having a 100% replication rate, I don't think is exactly the goal. The goal is to have, the goal rather is to see what the rate is, and then you actually will have a better sense of what we're dealing with, as opposed to just sort of blindly accepting, you know, published results are just, you know, the word of God, and must not be questioned. And we can't do, of course, any of this until we look under the hood and see how bad the problem really is. So just to summarize what the findings are, and of course all this is provisional, but one point here is that not a single list P was over 0.025. Now, why this is here exactly? There's of course multiple reasons that it could be. I mean, one is the standard P hacking explanation, but there's also, it also might just be sampling error. And from a purely statistical point of view, it's not surprising that we find the pattern that, guess what, and lower levels of smaller effect sizes also were less likely to replicate. That in itself is not shocking at all. It really just, in a way, of course, follows from inferential statistics. But knowing that we, are actually having trouble replicating at all above a certain rate is, I think, important. Why we're finding this pattern with the effect sizes is also, a question, I guess, into itself. There's a few possibilities for why that is. One possibility, which just doesn't strike me as particularly likely, but which has been suggested in, the New Yorker magazine. And whenever, the New Yorker says anything, and everyone sort of sits up and takes notice, even if it is like Malcolm Gladwell or whatever who's talking about it. But so we might just be dealing with Jonathan Schooler's decline effect, where all effects in the universe go down with time, and so maybe that's all it is, and there's nothing we can do about it. I think this is unlikely. Another possibility is that our replication teams are just bad. There's no fidelity in our replications, and it was the original researchers who were perfect, and all of the subsequent researchers who were doing a poor job, or perhaps had malicious intentions. I also think that's unlikely, but of course we can't rule it out. And in fact, it's possible that some of the replications weren't done with perfect fidelity. But I think that the main thing that we're looking at here is a publication bias problem. Now, we have some intriguing data on the rate of replicability within journal, but what we have really no idea about right now is what the true moderators of that are. Of course, one possibility is just that the people who submit to certain journals are all are more likely to be hucksters. I think that this is unlikely, although maybe we could give some psychopathy tests to some of the experimenters. But probably the better leads are what I have here. So one is maybe replicability rates change depending on what the topic is that you're looking at. Maybe there's something about the design of the studies that get sent to certain journals, or the journal acceptance protocols, or the statistical practices that are used for each of these journals. So what those actual moderators are, and this isn't an either or thing, right? It could be any or all of these things. But this we leave to future efforts. We'll be able to sort questions such as this one out. So, what you want to take away from the implications for the research practices, I suppose there's multiple things that one could take away from it. One is maybe we just need more powerful designs. Within subject designs would be one way of doing that. We might, following from the possibility that the actual topic under study affects the rate of replication, might mean that we should use different criteria for acceptance depending on the topic. I think that there's something that almost all of us can agree on, and that's that we need more policing, either self-policing or otherwise. One way, a really concrete way of doing this is to make it more standard to pre-register studies. This is something that is becoming more and more common, but it would be awesome if it became ubiquitous. And then finally, I think that given that we're scientists, at least nominally, I think just approaching everything with more humility and skepticism is probably a really a good way of making progress, right? Because if we're just sort of we assume that ever, then we're just going to be self-satisfied and probably not going to end up an accurate sense of what we've actually discovered. Certainly, the data that we have so far confirms the need for wider scale replications. I don't think there's any doubt about that. If we want to sort of also try to figure out like why are we getting this failure to replicate, there are many reasons for this. Only actually a subset of which includes the possibility that we have null results. But this is, of course, an important possibility. But there's also, it might be that, as I said before, that we have some sort of imprecise measurement, or the experimental design wasn't good. There could be random error. And following, I guess, from something that Kelvin talked about in the beginning, if this, to the extent that, and some of these replications were conceptual replications to varying degrees, right, where there's not like the exact same stimuli that are used, and certainly the samples are never identical that we're looking at. So to the extent that we fail to replicate something, this can tell us something interesting about the boundary conditions of the original effect. Now, of course, in the original papers, we're usually encouraged to kind of take the broadest and least conservative inference about what our studies mean, right? How much it extends to all cases. But if you change the specific, change the part of the country or part of the world where you take the measurements and you fail to replicate out that, well, what we thought was this sort of universal fact about human psychology actually is limited or bounded in certain ways. So it's not necessarily that it's just not true, like full stop. It's just that that the truth is bounded in a way that we was previously unanticipated. So having this replication rate in hand, once we have it, I mean, we have a provisional replication rate. But once we feel, even if we were to feel like more confident about like what is the replication rate in psychological science, that's not an end in itself. Knowing what that number is, it's really what you do with it. And I think that, I mean, for me, what's really cool about this data is the mystery, I guess, that it suggests about what's actually going on. And I think that it's particularly useful as a theory-building tool in conceptual replications. So figuring out what boundary conditions are, and also, of course, figuring out like what it is we're actually looking at. Are we looking at just a true null result? Are we looking at some sort of bias, a systematic bias in the way research is done? Or what is it really? And trying to figure, I guess, that out. So is it time for panic? I don't think so. Having this low and bad at science, and that that there somehow has been a failure here, really at all. I think that so there's just a couple of points to make. One is that the recognition for higher rates of replication is not something. It's something that is recognized in many fields. It's not just psychologists who've suddenly become aware that this is an important thing that we need to start doing. And within the replication project, there are similar efforts are now underway in neurodegeneration, in cancer cell biology, and there's also been some interest from economists as well. And to the extent that we can really get this going as that's something that's not just about psychology, because it's not, it's about science. I think that is really excellent. And also, just looking at like what we have so far, first of all, because we were talking about in the beginning, there's this, an incentive structure problem, wherein we're all incentivized as not just as these sort of like free agent people who don't have to worry about like getting or maintaining a job or grant money. There's an incentive structure to to just go for like sexy, interesting results and not to kind of plod along and do replications, particularly of other people's work. But in spite of the fact that there isn't an incentive structure for that, we've been able to kind of garner a massive community effort, even without that, towards these massive replications. And I think that that's really a cause for hope and optimism. We now have at least the beginnings of data in order to answer these questions that we want to answer about how psychological science is going. And I don't want to like get too meta on you or anything, but I mean we're in effect using science in order to fix it, which I mean maybe that's not meta, maybe that's just like tautology, but but we're using the power of empirical research in order to figure out what's going wrong and what's going right with empirical research. So thanks. I am done. I don't know if everyone's like microphones are off, but that
I am back now. Thank you. So thank you all four presenters. Much appreciated for taking the time. And I am now going to go throw up from watching the screen.
I'm really sorry. I apologize.
Yeah, come on.
So I'm sure we can do that better someday. But very much appreciate you guys taking the time to do this session for the broader team and for those of you that have come in to observe and send comments. Do keep sending these comments. The presentation is the 22nd, is that right? 23rd, something like that. It is, or at least the APS starts the 22nd. It's one of the days of the APS conference. So if you are watching this in the coming week and you have additional comments, don't hesitate to send them along. I sent along a link to that Google document that will have some of the collected comments, and perhaps the team, as they're revising, can note what things are taken care of in the updated versions so that you don't have to repeat yourself. The comments that are already there are going to be very helpful. Thank you, everyone that has already added those. And there will be much more refinement and nuance and everything else as as the comments come in and as there's more practice in getting ready for the session. So I think with that we can close, and we close right on time. So if anybody else has a comment they'd like to make that's in the attending hangout, feel free. But otherwise,
just to mention, the session is on Friday, the 23rd at 2:30.
Great. Thank you. Friday, 23rd, 2:30 Pacific time, right?
Right.
Good. Okay. Anybody else? That looked like something, Liz.
I was just going to ask if the four presenters wanted to stick around at all to give immediate feedback or not.
Great, we can do that. So we will end the session, the live session, and then we can have our private party. Good. Thanks very much, everybody.